let's have a look into the uncertainty principle in terms of the operators. In quantum mechanics, we have operators associated with the dynamical variables, and as variables give us the real value, so these operators are obviously Hermitian operator, which will give us real eigenvalue. Eigenvalue equation of this D operator looks like D operator. Dk is the eigenstate of this operator with the real eigenvalue dk, and this is the eigenstate. Now, as these eigenstates are orthonormalized, that means orthogonal and normalized, so they satisfy di dk equal to delta ik, this relation. This is the completeness property, and completeness property gives us the opportunity to write any arbitrary state psi in terms of the linear combination of these di eigenstates. Expectation value, according to the definition, expectation value for this state psi according to the definition, or rather it is called the axiom. Axiom is basically the starting point of something where the argument starts, and the definition looks like the expectation value of d equal to psi d hat psi divided by psi, and if psi's are normalized, then this denominator will eventually become 1. Now, experimentally I cannot measure this wave function psi, but experimentally I can measure the expectation value, because this psi is a state, it is not a physical object. So experimentally I can't measure this psi, I can measure the expectation value, then I can conclude about the property of this psi. Now, as this expectation value of this variable d is a physically measurable quantity, so I can measure this expectation value in psi and in phi also, where phi is just a modification of this psi. Psi is now multiplied with this complex number alpha, but this modifies the length of psi, but the state remains the same. What I mean to say is phi and psi are the same eigenstates. So expectation value, if calculated on this state psi, will be the same if I calculate the expectation value of the d on this phi state. Now, for phi, the expectation value is defined as phi d phi, and in the denominator we have phi phi. So in place of phi we are writing alpha psi, and in place of phi bra we need to write psi bra multiplied with alpha star, as alpha is a complex number. So my expectation value looks like this. It's alpha star psi d psi divided by alpha star psi. So basically we can see this alpha star cancel out from numerator and denominator, and we are left with psi d psi by psi. So it doesn't matter that whether we are calculating the expectation value on the psi or phi, because eventually we will land up in calculating the expectation value on psi itself. So now we can conclude that expectation value is the same for both phi and psi. Now, as this psi are normalized, we can write psi equal to 1. So the denominator becomes 1, and the whole expectation value, entire expectation value, is given by psi d operator psi. Now let's define the uncertainty in the dynamical variable d. This is the uncertainty del d, uncertainty in the measurement of the dynamical variable d, and this is defined as a square root of expectation value of d square minus expectation value of d and then square of it. This is definition, this must be positive, but first let's check whether the definition itself is correct or not. So my definition is del d square equal to d square expectation value of that minus expectation value of d and then square of it. Now as this is a square, this must be positive. The left hand side must be positive. So right hand side is obviously positive, but let's check it out. Suppose I have square of three numbers. This is 1, 4 and 9, which means it's a 1, 4, 9, which means it's 14. 14 divided by 3 will give me around 5, like it's about 4 point something, 4.6. But if now this is the expectation value or the average value of the square quantities. Now if I make expectation value of these three numbers, which is 2, and then I make a square of it, which is square, 2 square, which means 4. So definitely 4.6 is greater than 4. So if I do expectation value of the square of numbers, and then if I also evaluate the expectation value of these three numbers and then make a square of it, then definitely this is greater than this one, which gives me this right hand side also positive. And by definition for the state psi, it is written that d square sandwiched between psi and psi, and then d operator itself is sandwiched between psi and psi, now square of it, and this is a positive kind of thing. So expectation value as we have defined in my earlier videos. So this is expectation value of d equal to sum over k equal to 1 to n. This is dk psi mod square. This is alpha actually. This is done in the previous videos. And we are defining this dk psi mod square is as a pk. So d expectation value is equal to sum over k equal to 1 to n pk dk. Now pk is the probability of getting the particular eigenvalue dk, and as it is a probability, so it must lie within 0 to 1, and sum of all the probabilities is 100%, is 1, so I have written this. As dk is a real number, as it is eigenvalue of the dynamical variable, and this dk psi mod square is positive real number, so the expectation value of d is obviously a real number. Now let's start with the right hand side. I do not have this line in the right hand side. I will start from here and then I will reach here in this right hand side term, which is psi d square psi minus psi d psi whole square. First I will show that this first line will make me reach this line, and then I will show that this line is itself a positive one. So if I multiply all the 4 terms here, I will get this, and if I insert psi for each of these terms, each of these 3 terms, I will get psi d square psi minus 2 expectation of d. Expectation of d is a number, so I can take it from here, and I am left only with psi d psi plus the third term will give me psi d expectation square psi. D expectation is a number, so its square is also a number, so this can be also taken outside. I am left with psi psi for this term, psi psi equal to 1. So third term will give only d expectation square, and all the three terms will look like expectation of d square minus 2 d expectation into d expectation plus d expectation square, and I will eventually get this d square expectation minus expectation of d square, which is by definition equal to the left hand side, and left hand side we have del d square. And now I am going to prove that this thing is a positive term. So my second approach is checking this as positive. Before going into the derivation, I first take phi equal to d minus d expectation psi. So phi bra is equal to psi. Just making a dual conjugation of this will give me d dagger minus d expectation square. But d is a Hermitian operator, which saves me, and I get d dagger equal to d and this expectation star equal to d, because as it is Hermitian, so expectation value is a real number. So my phi bra is psi d operator minus d expectation, and phi is equal to psi. The thing, just I have put the expressions of phi here, and phi is nothing but the length square of phi, because this is just scalar product of phi with itself, which gives me the length square of the eigenstate phi, of the state phi rather. And as it is length square, so this is also positive. So as left hand side is positive, so this right hand side thing is also positive. So I have proved here that this entire quantity is a positive thing. Just one more thing before I proceed towards the uncertainty principle by using the operators. Just let me show you that if this psi is not an arbitrary state but it is an eigenstate for the variable d, then there is no uncertainty, which means if I measure the variable in its own eigenstate, there will be no uncertainty associated with the measurement of that particular variable. Let us define phi equal to d operator minus d expectation value psi, just I have defined earlier. This psi is now the eigenstate dk, so psi equal to dk, and now d operator operates on dk, and this is an expectation value which is just a number. And if I am measuring this expectation value on particular eigenstate, I will get the exact eigenvalue dk. So I get del d equal to 0. I get phi equal to 0, where phi is defined as this, and this gives me del d equal to 0, because del d square, I have just shown you that del d square is equal to phi. So when I measure the expectation value in an eigenstate of an operator, there is no uncertainty in the measurement. Now let's derive uncertainty principle using this operator notations. Suppose I have two variables x and y. These are two dynamical variables. Uncertainty principle tells us about the compatibility in measurement of these two variables. Uncertainty principle actually involves incompatible variables, for example position and momentum, as I have mentioned earlier. We cannot measure position and momentum simultaneously. We cannot measure x and px simultaneously. So for the time being, I consider x as position and y my momentum, for example. Now for position, we know that in quantum mechanics any dynamical variable actually correspond to an operator. So as position has real eigenvalues, so this operator must be an Hermitian operator, because eigenvalues of an Hermitian operator is real. And this is also a dynamical variable. Dynamical variable means what we can measure, and we get real eigenvalues as a result of measurements. And so for this dynamical variable, I have this y operator, and as this is a dynamical variable, so this is also an Hermitian operator. Let's define the uncertainty in del x and del y. Actually, uncertainty square, del x square and del y square. I have just used these relations where we have shown that del d square is equal to this phi. I have just shown a couple of moments before, and my phi was like this. Just let me show you once again. My phi was like this, and this dynamical variable d are x and y for this case. So here phi x can be written as x minus x expectation into psi, and phi y can be defined as y operator minus y expectation into psi. Let's use the Schwarz inequality. Schwarz inequality we have already discussed in my first video lectures of this operator series. And Schwarz inequality tells us that the length of phi and length phi x and length of phi y and their product must be greater or equal to the scalar product of phi x and phi y, their mod square. And this is by definition can be written like this. Mod square is already there. Let us define this quantity, this x operator minus x expectation value into y operator minus y expectation value as a new operator O for the time being. And now I am calculating only the right hand side thing, which is the expectation value of this O operator. And any operator O can be written as linear combination of two Hermitian operators. I have just shown that in my problem video. So right hand side is basically mod square of this expectation value. So this is my right hand side, and this mod square can be written as h1 expectation square plus h2 expectation square, because this is expectation of h1 and this is expectation of h2. Mod square is already there, and this quantity is definitely greater equal to h2 expectation value square. I mean, it is definitely not less than this quantity. If this vanishes, then this equality sign holds. Otherwise, this is always greater. So right hand side of this equation is greater than this expectation of h2 square. So if right hand side is greater than expectation of h2 square, then this left hand side is obviously greater equal to h2 expectation square, and this is nothing but this is del x square and this is del y square. So I can write in the left hand side that del x square into del y square is greater equal to this expectation of h2 square. And O is defined as this. Just let me recall this. So O, this is my O, and if this is my O, I can find out O dagger. And from the previous problem, the H2 Hermitian operator can be written as a linear combination of O and O dagger divided by twice I, and this is equal to 1 by twice I, the commutation relation of x and y. Let's show you how I write H2 equal to this 1 by twice I and the commutation of x and y. So I started with the definition of O, what I have considered here, and this is my O dagger. Let's make O minus O dagger, which is this all these 8 terms. One thing I would like to say that if this is expectation value into this operator, and expectation value is just a number, so this ordering is not at all important, but this ordering is important. This is yx, so I can't write it as x cap y cap, because these are the operators which do not commute. So these are 8 terms here, and out of these 8 terms, all the terms cancel out except this. So this O minus O dagger by twice I turns out to be 1 by twice I xy minus yx, which is equal to 1 by twice I, and the commutation relation of x operator and the y operator. This is a general relation. This is not for position or momentum. These two are general dynamical variables which do not commute. So for uncertainty, if we want to write the uncertainty from this relation, this H2 expectation square can be written like this, and on the left hand side I have uncertainty in x square into uncertainty in y square. That was the general uncertainty relation. It was not meant for position or momentum. It could be applicable for energy and time also. And in any special case, if I consider this x operator as my position operator and this y operator as my momentum operator, so right hand side, which looks like this, will become this one, because in place of x I put position operator, in place of y I put momentum operator, and we know the commutation relation of position and momentum. I should write this as px, and the uncertainty relation between x and px should be I h cross. I get cancel out. I have h cross by 2, which means I get h cross square by 4. So in the left hand side I have del x square into del y square. Right hand side I have h cross square by 4. So what I have arrived here is, this is the final concluding term, which tells me that the minimum value of this product of the uncertainty of x and p is h cross by 2. Let me tell you once more. The product of uncertainty in position measurement and uncertainty in momentum measurement is h cross by 2. This is the minimum value. H cross by 2 is the minimum value.